In this work, we investigate the shape identification capabilities of barometric tactile sensor arrays. Quite a few robotic researchers are using open-source optical tactile sensors to perform surface shape identification. Two examples are given here: the digit sensor from Meta, formerly known as Facebook, on the left, and the Tactile family developed by the Bristol Robotics Lab on the right. These optical tactile sensors are being used for shape identification due to their high resolution. Simply press the sensing surface against an object, take a snapshot with the built-in camera, then the shape touching the sensing surface can be estimated via image processing methods. However, these sensors are bulky and difficult to integrate with existing robotic hands, while image processing is usually slow due to their high resolution. We believe that a different type of open-source tactile sensors deserves a bit more attention, namely barometric tactile sensors. These sensors are essentially cheap commercial barometers on a PCB cast in rubber. They are only a few millimeters thin, can be easily extended, have much faster reading speeds than optical sensors, and the output data can be processed much faster. Hence, they have a much better chance to be integrated into existing robotic manipulation systems. But naturally, the high speeds are a direct result of low resolution. Barometers are spaced 8 mm apart and have no chance of identifying small shape features when pressed against an object. When an object is pressed against a sensing surface, nearby barometers pick up the pressure readings caused by deformations in the rubber layer. Unfortunately, a differently shaped object can cause the same sensor response under certain conditions, making it impossible to distinguish shapes via a single press. However, if an object is rolled across the barometric tactile sensor array, it is possible to differentiate object shapes based on the time series pressure readings from the barometers. Our goal is to answer the question: how well can barometric tactile sensors identify small object shapes via rolling? We utilize our previously developed robot hand design for rolling prismatic objects called the ICRA. One of its fingers has a barometric tactile sensor mounted. Notice how the hand dynamically adjusts its palm width to keep the fingers parallel to each other, which significantly increases the rolling range of the object. All objects used in our experiments are rolled across the sensor array, with the rolling procedure shown in this video clip, with the randomized starting positions and orientations. We carefully designed 9 different test objects, including cylinders and polygonal prisms with identical base edge lengths. To answer why some test objects have identical base edge lengths, it's important to know that the time series responses from each barometer contains positional information. As shown here, a sharp lateral edge of a prism causes varying pressure responses based on its position relative to the barometer center. Hence, we decided to have test objects with identical base edge lengths to make it impossible for the classification model to distinguish objects purely based on positional information. In addition, we also noticed that objects have different traversing velocities when rolled with the ICRA hand, which makes them easily distinguishable. Hence, we normalize all timing information to make object shape identification independent of rolling speed, which significantly increases classification difficulty. Finally, we only utilize 3 adjacent barometers for our experiments, effectively creating a fingertip-sized sensing surface of approximately 24 mm. We rolled each object 150 times with the randomized starting positions, resulting in 1,164 data samples after rejecting some unclean data. This slide presents 12 of these collected data samples. As we are only using 3 barometers, we plotted all sensor channels onto the same graph in different colors. To again highlight the difficulty of the classification task, we first look at the first row. These 3 samples are results from rolling 3 different cylinders, but they are extremely similar and hard to tell apart. For the following 3 rows, all samples in the same row are collected from rolling the same object. For example, samples D, E, and F are collected from rolling the same hexagonal prism. However, these 3 samples look nothing alike. As every data sample has around 600 pressure readings, which would unnecessarily increase the classification model's complexity, we implemented a feature extraction algorithm. This algorithm uses only 13 features to represent the shapes of the 3 barometer responses during rolling. In the end, we used the extracted features to train a backed tree reclassifier, achieving a 90.5% five-fold cross-validation accuracy after Bayesian hyperparameter optimization. Given the difficulty of our classification task, we can confidently say that barometric tactile sensors can identify object shapes with a remarkable performance if combined with rolling.